Okay, so how about if we wanted to predict the prices of the first three wines in our data set, right? What can we do? So let's go and check that first. So we will say wine here, run. And so these are the first three lines, years 52, 53, and 55. When you look at the prices, these are the actual prices of those. In our model, what are we using? So in our last model here, model 3, we're using AGST as input. If I scroll down, that means I can take these values for AGST, these first three values, use them, predict what the the price of the wine will be, and then I can also compare that with the actual price because I also have that available. The difference between them will give me the error. All right. So we already got the coefficients here, right? So this is our model, right? So with AGST. So what I can do is I can create a vector of these values. So these values here. So well, the easier way to do this is wine dollar AGST, and then I need only the first three values, like so. If I run this, you can see these are the first three values from the data set. Now if I run this model here, right, coefficient 1 is the intercept coefficient. Second coefficient is basically the coefficient of the AGST variable. So we are multiplying that with the AGST, and these are the predicted prices. So what do we see here? The first one is predicted to be $7.45. The actual one is 7.42, pretty close. Second one, the estimation is 7.21. The actual price is 8.03. The last one is predicted to be 7.47, while the price is 7.68. So those are the errors there, right? So I can say the same way I got this first three values for the AGST, I can get the first three prices, the first three values for price. So these are the actual prices minus, so let's call this spread for prediction. These are my predictions there. So minus spread will give me the distances between the two measurements. I mean the price minus the prediction. So these are the errors, right? So we talked about SSE, sum of squared errors. That would be taking the square of each. So we'll take the square of each and then sum them up. So this one, so these are now squared values, and we will take the summation of this. Or let me do this so it look easier. So let's use pipe symbol. Sum. So the squares are taken and then the summation is done. So this is the error SSE, well, at least for this first 3 points, right? So yeah, and we can do this for every single point in our data set, right? So the real thing would be like so. So if I go back here, so let's calculate the actual SSE. We will do that for every data point in the data set here. So right, so we are going to take the AGST values from this column. We are going to multiply that with its coefficient at the intercept, and that will be our predictions. You can see the prediction values here. The actual prices is going to be the whole vector there of prices minus the prediction, square them, and take the summation. SSE is 5.73. Okay. So the differences that we calculated in linear regression, if it is done on the same data set that the model was trained on, then they are called residuals. Okay, so it's still error, there's no difference, it's just the name residuals are being used. Okay. Okay, so if you remember, we looked at how to calculate the R² value. Can we calculate R² here? So let's try. What did we say? We talked about the base model, this SSE of the base model, the SSE of the fitted model, which is this one here, calculated it. So we need those two values. So what is the SSE of the base model? Right? So we need the SSE of the base model. Down here, okay. So what is the base model? We said the base model can be established by taking the average of the output value. We'll take the prices and then we will take the average of it. So the mean of the wines is $7.06 there. So that's our base model. So now I will need to calculate the SSE of this. So let's call this SSE underscore base. So my prediction is always going to be $7 here, and I'll take the actual prices from the wine data set. Actual minus the average, which is this one, right? So then I'll take the squares of these values, square, and then take the summation. So my SSE base, let's see what it is. It's 10.50. So now let's go here. So we said SSE base minus the fitted model SSE. And then this is the upper part of the division there. The lower part is the SSE base. Right. So this is the numerator here, and this one is the denominator. So this, if we run this one, we get 0.43. This is the R² value. Let's make sure that we are getting the correct value. So we worked with model 3. So if you look at the summary of this model, what you see here is these are the coefficients. If I look back here, look down, it's 0.435. That's the R² value. And that's what we calculated as well, right? So we did correctly. So that's good. And this is how you can calculate the R² value. Okay. So let's also now take a quick look at multiple linear regression. As I said, there's nothing special about it other than you adding more input variables. So let's do, for example, LM price. It's predicted using the harvest rate. The harvest rate plus. So if you want to add more variables, you would put plus AGST plus. Let's quickly remember what kind of variables we had. We had the winter rain, AGST, harvest rain, age, and so on. So let's add age as well. Go with these three, that's fine. So data is wine, right? Unexpected symbol. So why is it complaining here again? I accidentally I put a empty space there, so that's not allowed, of course. Okay, so this is our model. Let's save this. Let's call this model 4. Okay, let's look at the summary out of this. Summary. All right. So what do we see here? We see the coefficients of our variables. We see that each of them are significant. And also the R squared value has gone quite up. It's now 0.79. Right? So indeed using more variables did improve the model. So now let's check one more model. So in this case, let's say we wanted to make use of every single variable in our data set. Are we supposed to write each one of them like this and adding, pluses in between? Well, actually, we don't have to do that. If we are intending to use every single variable in our data set, we can say price tilde dot. So just a single dot there means use every other variable in the data as input. So we will say data is equal to wine. Right, if I run this, okay. Now let's look at the summary of this model. All right, so we have all the variables. You see they're all being used. You see their coefficient values, AGST and harvest rain, and also winter rain seem to be quite important or significant, as you can see. The others not so. R squared has gone up though. It is now 0.83, so that's another good sign. And the adjusted R squared is 0.78. In the previous case, it was 0.76. So what happened here is that harvest rain, AGST, and H were significant. So when we included everything, so some, first of all, the coefficients of those variables changed. So that's one thing we can observe, because again, there's always interaction between these variables. So when you add more variables, things will change, okay, based on how what kind of values the other variables take. Another thing that's might have caught your eye is this H variable has NA here. So what does it mean? Why is that happening? Basically, H was excluded from the model, so it didn't calculate anything about H in the linear regression model here. Why did that happen? Well, because as you can see, let's see here, year and age, right? Do you guys think it's correlated? Let's check on that again. So correlation between wine $H, wine $year, -1. 100% negative, very strong correlation. Why is it -1? Remember we said basically they are the same variable. They are giving the same information. So in that regard, they are same variable. So that's why we are getting -1 correlation there when something is older, right? So the age is more, then the year will be like earlier, right? So that's why when one is increasing, like age is increasing, the year should decrease, right? When something is older, it should have happened earlier than the other things. So that's why there's -1 correlation here. When it's a -1 or +1, basically we should not use both of the variables. We should only pick one, because there's redundancy in using both of them. And other than that, of course, there's matrix calculations here when getting to these estimates, to these coefficients. So when you have both same variables in your data set, your matrix, then basically the determinant of the matrix cannot be calculated. So that leads to issues, problems, and so on. So that's why H in this case was dropped by R. So we should either pick year or age. I think rather than year, using age makes more sense in my opinion. So maybe let's create a final model on that. Let's take this model 5. So another thing here, we can use minus to drop variables that we don't want to use. So I'm saying that use everything except the year. Let's not use year, let's use age. Age makes more sense. This is model 6, by the way, so let's change that. I will rerun this quickly so that we are back. We keep model 5 there. Okay, model 6. Let's see. So the AGST harvest rain, winter rain are significant. Age and France population were not found to be very significant by the model. Their p-values are very high. Yeah, adjusted R squared is 0.78. So this is a pretty good model here. Now I just feel, for example, France population, I don't see a very good correlation between that and the price. So let's drop that too. So other than year, let's also drop France pop there, and this is model 7, right? All right. Wait. Oh, sorry. I should not put a comma there. So minus here, minus France pop. Let's write it this way. Okay, perfect. So both France population and the year are dropped now. So now, as you can see, age became significant. Age wasn't found to be significant before, but now I think this model correctly represents, because I know for a fact that age does have an impact on the price. The older wines are more highly valuable in general, at least, you know, based on my limited knowledge about wines. So so this model definitely makes more sense. So sometimes, you know, well, not sometimes, in many cases, having more knowledge about the data will always help you in building more correct models. Okay. So yeah, so each of the variables are significant. They all have small p-values, so this is all good. So this model I'm very satisfied with. Okay, and adjusted R squared is now even better than before, because right, we are using less variables and we are getting almost the same R squared value. See, R squared was before 0.8294. The decrease by dropping France population is very small. The France population didn't have much of an impact. We are still at a high R squared value, and the adjusted R squared is even better because we are using less variables. All right, that's it. Thank you.